Yeah, correct my last name, Lavrijsen, but that's okay. Nobody can pronounce it. So cppyy. Okay, the first thought is of course yet another C++ Python binder. There are like a dime a dozen. This is true. It's yet another one, but it has a niche that is different from anything else that you will find out there, which is that it creates bindings at runtime. And my argument that I'm going to make during this presentation is that since Python is all runtime, no matter what you do, anything in Python is runtime. So runtime bindings are way more natural to do things at compile time. And the reason I'm here at this particular meeting is that the C++ side runtime nurse is provided by Kling. And that's of course why we're all here for this project. Another thing is it's a very complete feature set. So yes, it's yet another, but it's not just C with classes and declared yay success. You know, can I do all of C++? It has been around for basically its roots started in early 2003. So it's been around for a very long time. And its feature set is very, very complete. There's a very wide range of users trying the craziest stuff. And so there's these days very little that is still missing. It has good performance on CPython. I will get to that later in the talk, as well as great performance on PyPy with the caveat that feature support on PyPy is lacking CPython. There's a few reasons for that. One is that it's harder to develop for PyPy than it is for CPython. The debug cycle is a lot slower. But also there's simply more users for CPython, so there's more feature requests on the CPython side than on the PyPy side. I also add as a quick note that for the people here online who are HEP users, there is a version of cppyy inside root, but it is an old fork, and it will not run all the examples that are in this talk. It doesn't work with PyPy as far as I know because of some changes that were made locally, and it's actually worse performance. So I'm not considering this version. What I'm talking about is one you'll find on PyPy or on Conda, version 2.1 being the latest. You can find all the source code, as everything is open source on GitHub. I've recently moved from Bitbucket, and the documentation is online on Read the Docs. So I want to start off with a range of examples of why runtime behavior is, to my mind, the better way to go. Start with an obvious one. Let me just remove my face here. The runtime template instantiation. So Kling is capable of instantiating C++ templates at runtime. So you do not need to pre-instantiate and compile templates in order to bind them and then provide them to the Python user. This prevents a lot of duplication of standard classes. Think everything in STL, like std vector of double, std vector of int, whatever you have. There's no combinatorial explosion. Think of projects like Eigen, where you might want to mix numeric types. And of course, it's something that you cannot do in any other way. It supports the templates of user classes. So if you have your project and you bound this to Python, you can take care of all your own classes. But now say you have some graphics application or a user interface application, the user comes with some classes, you know what you're going to do. You have to provide support within your project to generate similar bindings for your user classes who may or may not be capable of dealing with these technologies. In this case, it's on automatic. To give you a basic example, say on the left, I have a class, just some my class, nothing special, carries an int, and that's it. I can load this into cppyy either by including the header or using the autoload mechanism. And then I can just create a stud vector of this my class just on the fly. Don't need to do anything beforehand. This will just work. You can see over here, I can use the mPlaceBack method, which is templated, and use the implicit conversion from the integer, and then use the constructor that you see on the left, the my class constructor that takes an int over here. That will just work. As you can see, the length of the vector is correct, and I can just iterate out the contents of my vector. And you see that everything has been properly added. So that's fun. Another thing that you can do is with Kling is that you can generate C++ and compile this with the JIT and therefore add features at runtime. So one important feature is for cross-inheritance, where you use trampolines to call from C++ to the virtual table that C++ requires for inheritance into Python. This way, any proper C++ base class can be inherited from. So it needs to be a base class, can actually be used as a base class on the C++ side, obviously. And then you can use it. You don't need to select beforehand when you write your bindings which base classes you would like to provide to the users to inherit from. So only methods that are actually overridden will receive trampolines. This is performance benefits because you do not need to check at runtime whether the method was overridden or not. There's also no overhand added to the bound base class. So this again, there's nothing that will change For the classes that you bound, it's all on the user side. The classes that are generated this way, a memory management, copy, move, assign, destruct, everything will work as expected. So as an example, we keep the same my class, and as you have seen before the test, this virtual method called add. Over here, just add the integers to the data that it has and returns the result. Now I'm writing a PyMy class, which I inherit using normal Python inheritance syntax from the C++ class. I override this method add. And as you can see, if I now instantiate the PyMy class and call this method, in this case I use 2, instead of adding 2 plus the original data, which is 1, and getting 3, I've implemented the method to multiply this number by 2 first. As I get 2 times 2 is 4 plus 1 is 5, which is indeed the answer that I get over here. So this is all functional. There's a small caveat for multiple inheritance. In Python, this changed between Python 2 and Python 3 and how this is handled. And so if you want to do multiple inheritance, you have to use cppyy.multi and then specify the classes rather than specifying the classes directly. And this is again purely to make sure that your code is portable between Python 2 and Python 3 if you still care about that these days. So then the obvious next step, and this is what users will always do. So if constant inheritance works from Python, and this allows C++ to know about classes, and these classes are fully functional, they're identifiable, the memory management, everything is good. And if C++ classes can be used as template argument, well, what can you do? Well, this is emergent property that immediately becomes available, which is that now you can use Python classes and templates. Oops. Where is my, yeah. And so the same example, now I'm adding a constructor to the PyMy class that takes some extra data. So I'm calling the base class constructor as is required by the way that Python deals with base classes. I store this extra data, and now in my method, I'm adding the original data, the extra data that's stored in the Python constructor only, so C++ has no knowledge of this, plus the other method. Now I'm creating a std vector of PyMy classes, and I'm pushing back in a PyMython class with these two entries to its constructor. So on the Python side, this is a temporary. On the Python side, this thing after this call is done. The only one who has no knowledge of it is the C++ side. And now I take the last element in my vector and I call the add method, in this case for 17. And as you can see, the answer that comes back, 80 is 2 times 17 plus 4 plus 42. 80 is indeed correct. So the C++ side has kept the PyMython class alive. It is the original one because the entity constructor, which only lived on the Python side, is still around. And the method simply works. Another feature that is good to deal with, clean instantiate the templates at runtime. We've seen this, but if you want to instantiate a template at runtime based on the argument types, often it's not quite clear which type should be mapped. To give a very basic example, on Python you have this type called int. It is actually an int along in Python 2, but in Python 3 there is only int. In C++, however, if you say, okay, I want an int, the question is, okay, what int? An int 8 and uint 8, blah, 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 all the way up to uint 8 64. There's this whole range of integer types that you can choose from. Which one did you mean? So the solution then is to automatically fallback as needed. To give an example here on the left, you will see just a simple, a simple method that takes an argument and returns that argument. Then it's templated on the type of the argument, and so this in principle should just work. So we work with this, and then look on the Python side and I check the type of the value 1, and not surprisingly, this is a type int. I call this to my method and pass my 1, and I get a 1 result. And this is easy, right? Because you have an int on the Python side, you got an int on the C++ side. As you can see, the doc string that has been generated for this method after it has been instantiated is indeed, that's what we have. We use the type of int as the type for the template. Now I have a different variable, a different value that is 2 to the power 64 minus 1. Now this is not going to fit on any of the major platforms because ints tend to be 4 bytes. And so on Python, it's still going to tell you the same thing. I have an int right here. And now I pass this, and lo and behold, I still get the right result back. And what's going on? Well, you can see if you look at the doc string under the hood, because the value didn't pass to an int, it has actually changed the template parameter to another int that will actually work for the value provided. Now, there's a limit to this, obviously. Now, if you do 2 to the power 65, it's going to fall apart because C++ is going to provide me an integer type that will work for this. But up to this point, all these methods will be transparently correct. Callbacks is another major item, just like with cross inheritance, in order to call from the C++ side into Python. Here, just like with cross inheritance, CleanSheet compiles generated wrappers. They're type checked and memory management and memory managed. Because of the type checking, you can get Python exceptions if you call these callbacks. And all this is traced back to Python and C++ if there's an error. This is all properly managed. Python manages the lifetime because this is where the method actually lives. C++ manages the resources of the generated wrappers. And so there's this one caveat that if you store the pointer to the Python function that you sent to C++ in a C++ object, then you need to manage manually the, sorry. Oh, babe, Papa's in a meeting. Then you need to manually manage the objects on the Python side. Typically, it's not hard because you can just store them at the callable where you pass it as an argument, but this is one thing to be aware of because there's no other way other than just leak the resources on the C++ side, which is another common approach, but I chose not to. It supports both C++ function pointers as well as stud function for callbacks. A Python can pass any callable. It doesn't matter. It can be a function, it can be a lambda, it can be an object that implements the _call function. And of course, you can also pass bound C++ functions and methods, but in that case, it won't bother with generating a wrapper because you can just unpack the C++ function pointer and pass that. So here's some examples. I have here a function pointer that I use as an argument to this call pointer function. This takes an argument, use this argument and return the result. The exact same idea with the stud function rather than a function pointer. I pass a const reference to this function pointer. I give it an argument to call and I call the result. And as you can see here on the right, in the Python code, I write this Python function f. The nice thing about using a function over lambda is because now memory management is easy because it will stay around. Nevertheless, I can also do the same thing with the lambda as long as I do not store it on the C++ side. All that's going to be good. And you can see that the values correspond to the functions we have in being called. So the next step, so this works for function pointers and stud function where you know the types, you know exactly everything. Well, what if you now have a templated callback? So modern Python 3, and we're talking about, I think 3.5 or 3.6 where they started, supports the concept of annotations. And this is very commonly used these days in any modern Python project. And what this does, and I'll show an example from that in a moment if you're not familiar with it, this is type information that can be used by IDEs, static type checkers, whatever, for all kinds of purposes, whether it is to provide hints in the IDE or to check whether the results are correct. There's also all kinds of useful ways of using this information. It is, however, not actually used by the interpreter. The interpreter will need to store the information in the dictionary, so it needs to be something it can deal with. Other than that, it doesn't care about it. More recent version of Python recommend that you just use a string because this is easy to put in the dictionary. But there's also type modules where you can use specific types such as unions and whatever to specify that there are multiple types that can be passed through an argument, etc. In the case of C++, if you do an annotation of a function with C++ types, you kind of have to use strings for the compound types. If you have an object star or an object ref that you want to take in or return, you cannot really represent this as a Python object, so you're kind of stuck with a string. Otherwise, if you return things by value or use basic types such as int or float, you can just use the original type. But strings is by far the easiest to deal with, and this is what you see most often. So now what we can do now is use these annotations to instantiate templates. And this includes, of course, bound C++ functions, but by definition they're annotated, meaning you have the C++ reflection information available to Cling, which gives you the same kind of power. So here on the left, we have a similar example before. It had a call pointer and call func, but now we use a template. So we have some function f that takes some arguments, which are represented by the argument pack u. The callback function itself. So the function calling the callback itself takes some additional argument called a, represented by the argument back a, and then returns some type r. This is the exact same examples as we've seen before, just now it's a template. As you can see over here, if you just look at the body of the function, you could actually derive what is what, right? Because you would know that the types of A match the types of U, but just looking at the signature, you wouldn't know. And so the way that this gets resolved is on the Python side is here on the right, you have annotations, such as over here, where A is promised to be an int, and the result is promised to be a double, which is indeed the case over here. Now I can use this, this information to instantiate the template and get the proper result from the call. There is on the left, if you look at the body of the function, which is in principle available, you could derive that there's this relationship between U and A, so you could maybe fudge something over there. But there's no way on earth that you can get the return type from the Python function without executing it if you do not have the annotations. So that is the thing that saves you here and makes this possible. And then a similar example, just to see that the argument packs work for two arguments in a return of an int, and the same result, this just works. Some more runtime features: automatic downcast and object identity. So cppyy always casts objects to the known derived type. This involves a fake base and retrieving the C++ ITDI. There is some custom ITDI implementation has some Microsoft Windows, because there are problems with the code that the Clang JIT generates, even in Clang 9, still around. But this is all functioning otherwise. As well as the ability to preserve the identity of the Python proxies in the C++ instance. And this really makes it easier to do resource management, because you do not have multiple proxies pointing to the same C++ instance, and so you reduce the risk of dangling pointers. It also guarantees that the hashes are equal for dictionaries and all kinds of reasons why this is very useful. And then most importantly, as we saw before with the cross inheritance, where the assignment and copy constructor is properly working, and making sure that the identity is the same, makes it really easy to implement these features. So as an example, I have a base class and a derived class. The derived class derives from the base, and have a function where I pass a base pointer, get a base pointer back. If I actually use this on the cppyy side, so I create a derived class, and I pass this derived class to this function that takes a base pointer, returns a base pointer, I actually still have a derived class back. Not only is that one downcast to the derived class, if you check whether this is the same Python object, you will see that this is indeed true. This is the exact same object that you get back as you put in. Exceptions in this has been a long story to arrive at the implementation where I'm at. So Python exceptions are not object instances. In any other class in Python, derives from the base class object, unless you're dealing with really old Python 2 versions. But exceptions do not. They derive from base exception, and there's reasons for it. There's less overhead in that class, and they have a special case when the application shuts down with the system exit exception, and so they fall in a separate hierarchy. So you can't really use the two even where you want to. The cppyy had to marry the two concepts, because it is a normal C++ class that you want to bound like any other. At the same time, you want to be able to use it as an exception. There was an alternative, and we've played with this for a while, which is to map Python exception classes and C++ exception classes. There are a few that match, like logic error, for example, but by and large, if you go to the whole structure of different categories, there isn't really all that much overlap. And this runtime error is another one, and it kind of ends there. Everything is sort of the same, but not really. And so I got a chat here. Yes, like I say, I'm cheating. In answer to the chat, it's like I said, in Python, this is on the C++ side. If you look, where's my thing that's going away? I'm looking at the chat button over here that is not going away. If you look on the C implementation of the different exceptions, the exception-based classes and the normal base classes, you'll see that they are not backed by the same base class between the two. Let's go over here. I'm looking at okay, close close this window. I'll go to that. They on the C side, looking at Python interpreter implementation, they're not the same base class between the two, and so you cannot pass one on the C side between where you're expecting a normal Python object versus an exception. I can show you the code if you want. They are not the same thing on the C side. So what was chosen instead of mapping the categories is to preserve the actual Python C++ exception types. And the nice thing about preserving this is that you can actually allow them to cross multiple language layers. So you can go from Python to C++, Python C++, and if you return back into C++ from Python, you still have the same exception round. In some cases, you kind of forced to copy it, which in the case of exceptions usually works. Otherwise, you can default back to just the base class, that exception, and move from there. And this allows you to have a trace back through all the language layers and to see the full stack in the end. There's one caveat: you cannot on all platforms mix compiled and jittered exceptions. Looking at your Windows, hopefully this will be fixed in a future version of Clan. So what does this look like? Say I have this my exception class here on the left, and I throw this error, and and I import this into cppyy. I call this throw error function, and I can actually capture it as the exact type over here, and then print it. Unicode is another one, mostly because of the heritage of Python 2. So Python Unicode encapsulate both the code pointer and the codec, so you know what you have if you have a Unicode object. It defaults to UTF-8, but you can have any codec that you like. C++ is just all over the place, again, because of historic reasons. I'll get another chat. People can also interrupt me if you want.
No, I don't want. I just wanted to state that also Apple M1 is terrible there.
Yes, I know. I've recently started doing Apple One, and to be honest, Python support for Apple M1 is still pretty flaky itself. Basic packages such as NumPy, SciPy, etc. Not quite there. You can install it with your favorite thing like Macports or whatever, but if you use PyPy, it's not quite quite there yet. Anyway, the C++ is all over the place, mostly because of history. Many people still use just a string to encode, byte encode the Unicode and send it around. So you have some object without a codec. So you look at some data. What is it? You have code points without a codec. You can use wide narrative types with an assumed codec. But the result is platform specific. In fact, YChar itself is platform specific, looking at your Windows. At the same time, so the result of this is that the type string in Python is not C++ string, even though you use it the same in pretty much all over the place. But developers still want to use these interchangeably, part because of the history of Python 2, part of it's kind of natural to do this. I'm going to ignore the chat for now. I'll get to that later. People can interrupt if they want. So there's an example. I have on the left, I'm creating such string objects from differently encoded Unicode. In this case, the character is Zhongwen, so Chinese. One is UTF-8 and the other one is GBK. Over here, the moment that you print it, you need to make a decision. Okay, what do I have? All the way up to the point, you can do whatever. You can just store internally whatever you want, but the point of use, you need to make a decision. If you don't know any better, you will just assume it's UTF-8 because it's the safe assumption on Python in most cases. And in this case, if it is indeed UTF-8, it will just work as expected. If it's not, you will not be able to decode it, and you get some different result over here. In this case, this result is not what you expected, and this is where you have to provide manually the extra information that indeed this is GBK. Now you can decode it and you get the actual result. So what this allows you to do by making this assumption of UTF-8 when you do not provide any information, it allows you to use stud strings as Python string, anywhere where this is reasonable. And then if you have an application that does something different, does something unexpected, you provide the manual information and it's still functional rather than failing with an exception. There's much more, and not directly related to runtime as set. The whole binding is pretty complete in classes, functions, static methods, everything that you can care about. There's also a growing amount of low-level C support. Not proud of that, but people come asking for this because of legacy applications. So you can do low-level memory management. Arrays is growing and growing, which is kind of sad because I was hoping that NumPy would take care of it. But it turns out that, with more information that they can extract from Cling, you can actually help along with better offset calculations, some memory management that you can do in specific cases, and that's being added. And of course, if you really want to, yes, you can do pointer math. Some more fun stuff, debugging support, for example, you can turn a segfault into a Python exception. Of course, caveat is after a segfault happens, anything after that is pure luck if something works. But if the segfault is local, such as, for example, the references of a null pointer, you can easily turn this into a Python exception. And the nice thing about this is if you have a segfault and get a traceback from C++, you will see all the Python interpreter C function in your traceback, which is not particularly useful. Whereas if you have a Python exception, it will trace back through your own Python code that you will actually recognize and be able to debug this much faster. It's an on-off feature. You enable it in case you're accepting segfaults, industry run it and then see it this way. There's ways of making custom Pythonizations. You can freeze binary distributions using PyInstaller, CMake fragments for projects, etc. And see. Read the doc. So I have a quick look at the chat questions. Oh, those people are not happy. All right. Yep. So I hope I've convinced you that doing things at runtime is great, but what about performance? Because this is the usual reason where people say, okay, this is a bad idea because you're going to kill performance. Okay, let's try this out. Well, let me make one remark. There is no fundamental reason why CPU performance will be different between doing things at runtime rather than at compile time, because everything in Python is runtime. So there is no such thing as creating bindings and compiling that. If you compile bindings, all this really means is that the recipe to create the bindings at runtime is compiled. It's not the actual bindings themselves. And so there is no fundamental reason why any binder, regardless of what approach, would be slower or faster than another. It's just a matter of the implementation. The one caveat, though, is that there's this heavy Cling LLVM dependency. Excuse me. There's about a 25 megabyte download cost to download Cling, as well as 100 megabyte memory overhead. And the installation is getting more complex. And if you try to build this yourself, this can be rather complicated, especially if you try this on a laptop or whatever. Now, 25 megabytes sounds like a lot, but there's also people who send PowerPoint presentations over email that are larger than that. So at some point, do not worry. 100 megabyte memory overhead, do you care? Depends on your application. Some people do, some people don't, but there it is. So doing some very basic performance tests. Now we use two examples. One is just an empty call doing absolutely nothing. The other one is an overload. And this example over here, just a simple loop. Excuse me. Calling the same thing over and over again for n times and dividing by n, and you get an answer. The system specs over here, you see I have a terabyte of RAM, so the 100 megs more or less I don't care about. I use GCC to compile the out-of-line functions to be called, but I will use Cling to do the actual calling. Use PyTest and PyTest benchmark to run the benchmarks. And I'll use cppyy 2.0 for PyPy 11, see all these versions, one from PyPy and the other one from the system. So here's some examples for the empty call. So this is this guy over here, just nothing, albeit out of line. So using Cling, Cling has been hacked to enable optimization, but the function itself is out of line. So the overhead is calling into the shared library where this function actually lives. And execution time comes down to 1.5 nanoseconds per call. Using cppyy under PyPy, you come down to 16. And the reason why this is larger is mostly because PyPy actually releases the GIL when entering C++ and then reacquires it. And that's where this extra overhead comes from. Using Swig with the built-in option, which is not the default, but this is possible to use. you will get 27 nanoseconds. The reason why it's not the default is because this way the functions are not first-class objects, which makes them less functional, which you may or may not care about. But if you do it this way, the advantage is that there's a fast path through the C interpreter where you can just flag that this is a function that doesn't do anything and doesn't take any arguments, and it will go quicker to the interpreter with fewer temporary objects created along the way. And this is why I get this level of performance. Then cppyy with CPython as well as PyBind 11, they're hampered by the creation of the temporary objects in the Python interpreter because they both use closures, which gets you 68 nanoseconds per call. And that's with default, which has a Python layer. You will see they get this lower performance because now you're executing some Python code on every call, and you end up over here. But my main point is there's no obvious reason why a static binding over runtime binding will give you any performance benefits, and you can see that here in the results. Now the overload test, Kling doesn't. Oh, come on. Kling doesn't get phased. You can see over here the call is the -6 because now the unit is milliseconds rather than nanoseconds, and so it's just as fast as before. Which, if you look at the example, is kind of obvious because the object is known, the method is known, nothing is virtual. You just call it, and the only reason why it's a little bit slower than the empty call is you're passing two arguments. One is the implicit disk pointer, and the other one is the integer. And so it's a wee bit slower. But other than that, you're still at the nanosecond level. Now with PyPy-C, you see already significant slowdown. It's still the fastest of the bunch. The reason it's slower is because there's the Python instance type checking applied. Because in Python, you could conceivably call this method and then change the instance underneath, so the type needs to be checked. Since PyPy does this at the start of a trace, if you have multiple methods, it would actually see a benefit over there because you would only check it once. The other binders would not have this benefit. Then with CPython, cppyy-CPython, you get 1.25 milliseconds. Strict with built-in, again, because of the fast internal pass, 129. Strict with defaults, where you have a piece of Python that is part of the overload resolution. You get a slowdown, and PyBind 11, which does not have a runtime, and it's therefore much harder to do proper type checking, comes down to 7 milliseconds per call. Then a quick overview of the implementation, how things work. So the reason why this works so nicely with Python is that Python offers hook pretty much everywhere throughout the code where you can customize things. Think about meta classes for class creation, the get attribute method for resolving attributes, get item, call for template instantiations, etc. And so these hooks are all re-implemented, and they allow to do lookups into Kling whenever something is not resolved or any of these guys are getting called. Now, the first initial look is always string-based. You always start out with something on the Python side that does a lookup of a string into some dictionary or some argument of a call, and this then goes into Kling. Afterwards, once you have something as an opaque handle in Kling, you can speed things up. You can move away from strings, but the first one is always string-based. And then access to C++ code is provided either by address. Say you have some variable which you know the type of. You will use the address of it, which may be offset from a class instance or a wrapper that you generate. And the reason we're using wrappers is that it more easily covers esoteric cases. We'll come back to that in a moment. And then there are generalized interfaces as part of these wrappers to make the calling much easier. So as an example, say I type cppyy.gbl. GBL represents the global namespace. And I ask for my class. Now, it could be that I looked at my class before, in which case there will be an entry in the GBL dictionary, and my class is known, and just return my class and done. Now, if it is unknown, Python will trigger the $getAttrib method, and this is re-implemented to then look into Kling. Two options: either Kling doesn't know either what it is, and then raise an exception, or it knows what it is and will tell you, okay, this is in fact a class. In that case, you can create a proxy using reflection information from that Kling provides, create all the methods and data members of the class, and you can return the my class, which can then be instantiated and used on the Python side. In the case of templates, instead of getAttrib, you use getItem, the square brackets, or call the parentheses if you have explicit or implicit instantiation respectively. The proxy creation you see over here is set to relies on Kling provided reflection information of all the details, but wrappers are only created on the first time you actually call a function. Similar for a call example. So now I have my class. I create an instance. Oh, there's a typo over here. It should be m.calc. If calc is a template, then you're not done yet because you need to find the actual template based on the type arguments. So you create an explicit template and you go from there to Cling and say, hey, do you know this explicit template? If not, you raise an exception, you're done. Otherwise, you have a function. Or if it's not a template to begin with, but a function, you end up at this point. Now you can generate your wrapper. You can call the function and you return some results. Now the wrappers of the generator and the C++ code, they are using wrappers in order to cover a range of C++ thingies that are otherwise very hard to generate if you were to deal with the ASD or I level. Think about the linkage of inline functions. Think about the use of operated operator new or default arguments that might be some complex object that is pulled in because of a using of a namespace somewhere. The lookup of operators, again, you can have Koenig lookup, and so there's a whole range of places where an operator can come from according to C++ rules. It could be that it has to be instantiated for a template, etc., etc. So by dealing with this at the level of generated C++ and then compiling the wrapper, Clang will take care, or the Clang JIT will take care of all this, and you don't need to deal with this on the Python side. That said, if it's determined that the case is simple, that this is a simple function call, for example, here calc is a simple known function call, and you can go over here immediately, then in the case of PyPy, we'll actually use direct foreign function interface, a direct FFI, in order to bypass the wrapper and get this speed benefit. It needs to be said that for CPython, the wrapper isn't that much of an overhead that this is going to matter, whereas for the PyPy tracing JIT it might, which is why that optimization is there. So conclusions, just to come back to after all the good things I said, to the limitations are there, just to keep it in the back of your mind. This is complex and heavy Cling LLVM dependency, both the download and as well as at runtime. The other big negative of using Cling is that all C++ code enters a single global translation unit. This is most of the time not a problem, especially if different codes live in different namespaces, but you can get a significant slowdown when using templates in heavily templated libraries that have also a lot of structure. I'm thinking of Icon, I'm thinking of PCL. For example, in Icon, you have a sparse and a dense set of functions. And it's easiest if you easiest on the C++ compiler if you keep those separate in your code, and therefore Icon itself is split up. PCL even more. There's like 30 different subdirectories to keep individual templates separate, so that the compiler does not need to consider them all at the same time. In the case of Cling, however, they all get thrown in the same translation unit, which leads to a significant slowdown when using such templates. Using CPython and PyPy is significantly behind CPython in terms of feature support. There's a lot there, but it's about half where CPython is. There's no MS Windows support for Conda at this point, and there's significant Clang JIT limitations on MS Windows, and as Axel mentioned, also on MacBook ARM at this point in time. Our current focus is to see whether we can add CUDA support, GPU support to cppyy based on the work presented earlier at these meetings, to get the implementation on PyPy on par with the one on CPython, and in particular to simplify the installation distribution. Kind of holding off on the last one because you'll get more users who are not that technically sophisticated. I'm working with a group of architects, for example, at the moment, and they're finding all kinds of little bugs in the use, particularly again on Windows. And it's a lot of work to keep up, and it's about as much as I can handle at this point in time. But soon enough, this needs to be simplified so that you do not need to have a compiler on the user side, for example, on installation. Don't need to build anything there. There are solutions for this. There are ways to deal with this. You can fix all this to show you can do it. To just not quite ready to put this out yet. So in conclusion, I hope I've convinced you that runtime Python C++ bindings are much more functional than similar static approaches, but without loss of performance in terms of view, but with a little bit of memory overhead. And that's all I had, and I'll open the floor to questions.
Thank you, Wim. Questions or comments? Okay, maybe I can start. I have 3 questions. So the first one is, what is the way that you normally debug things that do not work? Is there some impedance mismatch between C++ and Python when it comes to debugging, and if the issue is somewhere in between these layers?
Yeah, so there is, I forget the exact syntax, it's in documentation. You can enable debug in cppyy, but it's hurting you is that debug information is generated by the JIT isn't fully functional. And again, looking at Windows, this doesn't always work. So you cannot just enable -G on ClingX or ARCs and get the information from there. What I have for most support are things like here with the segfault that you can go through to the various layers and get a full traceback between the different languages, because that's the most complicated case when you have callbacks and cross inheritance, and you have, say, some user interface implementation where you implemented some derived class that does whatever. If you just get a segfault somewhere in the middle of your user interface doing stuff, you're lost. So that is one. Yeah, there's the Python debugger that will work well with this. So that you can do. The only thing that really hurts you is not having debug information from the Clang JIT.
So you can, if you have like a crash in the somewhere in the cppy layers, then you can just attach GDB, and then assuming that the JIT would have debug symbols, you can debug the whole thing, right?
It is theoretically possible that the crash will be in the cppy layers itself. However, that is highly unlikely at this point in time. Most bug reports, when there is a crash or anything, it's really not in the cppy layers. You will find it in either some C++ code that is called, or there will be some issue on the Python side, but not in the intermediate layer. First of all, the layer is thin, so it's not really where it's going to happen, and it is pretty easy to do error checking on Python. So there are very few cases that something happens over there. If there is a crash caused by the bindings, it tends to be in Cling, and this is super hard to debug. The real problem for debugging that is because the size of the binding is kept low, but not including debug information, since the array doesn't work with the Clang JIT. So once you hit the wrapper function, you're lost anyway. But in Cling itself, in order to rebuild this locally, this takes a lot of time. So my machine that I did the test on, I can build it in 4 minutes, but most people work on a laptop. You can wait half an hour for Cling and everything to build. And so this is not easy to work with. And I don't really have another solution for that other than, submit a bug report and I'll have a look.
Okay, thank you. More questions and comments?
Yeah, I have one. I raised my hand, but I'll just lower that again. Hi, Wim. Thanks for the presentation. You were showing how you update Python's view on a function name if it's a template and some other template instance gets called.
This one?
Maybe. I think it was a slide before where you were showing the type info of a certain function.
Yes,
that gets reinstantiated differently, and then, right, exactly. If I remember correctly, you're using the name of the function as a key for looking this up. Does that also mean that you now forgot that you had pass t of int instantiated, or how is this done internally?
They both remain around.
Okay.
But the second one will get preference for integers from this point on.
Okay, so right, that was my next question, because I remember that the Python interpreter and your setup of cppyy was actually aiming to have calls in hot loops really, really performant. So you're saying in hot loops, you're not checking again and again the whole instantiation machinery. You assume that the call to pass t is of the same type as before.
So what is happening under the hood is you get this value. This value on the Python side is boxed. It is it's not actually in Python 3 an int anymore underneath. If you were to break it open, look at the underlying C structure, there's not an int there. You need to extract it. So you need to call a function to get the int out of the object. And that has to happen everywhere, anytime, whatever you do. The reason why you make this changeover, what happens is you try to get an actual C int out of this value, and Python says, you know, overflow. And that's your cue to move on and move to a different type. And so the next time you come over around, you know, it's not going to overflow unless you have 2 to the power 65. And as explained, that is when I'm also at a loss and say, okay, sorry, nothing I can do anymore.
Okay, thank you.
So there's just, it's the Python method things, right? You try and then you fail, and that's your cue. It's not you check first and then move from there. And
yeah,
so this
that
is
makes
why
it
there's no
more
slowdown.
Right, that makes it more performant in hot loops as well, right?
Yes. In fact, in Python, it has a trick that if you have a failure, it will actually return the -1 value rather than you have to check the exception also for performance reasons. All kinds of tricks that the Python interpreter folks have done to make this as fast as possible, but you cannot get around the unwrapping. And so that's what you use for the error checking.
Okay, thank you. Sorry, I did not see your hand up, Axel. More questions and comments?
I need to look up the cAPI call and show Jim that the two are indeed different.
I still have another question if I can.
Sure, go ahead.
You were showing that you have O2 enabled.
Yes.
Is that just the CI factory O2, or did you find the bug?
The bug. So there's a couple of things that that are hidden behind it. So this part of the simple yes enable O2, which is part of Cling extra args, as well as setting the op level 2 when you create the pass manager. But in addition, the way that Cling was set up before, it doesn't actually enable inlines. Yeah, and so exactly. I have some other changes that come over there. They're in my list of patches that you'll find on GitHub. My main point is that, you know, I'm not cheating on C++ when I use Cling to do these calls out of convenience rather than using GCC and just running a function on the shell. Just by using Cling, I could use it through PyTest, and that make my life easier. But regardless, I don't think that the numbers of 1.5 nanoseconds per call across a shared library is unreasonable in any case.
No, no, totally. Yeah, it's great. No, but it's the inlining. It's the inlining I was referring to, and I'm glad to hear that you enabled this. Good.
Yes, but it's not a factor over here because I explicitly put this function in a shared library not to have it inlining, because otherwise, if we have an empty function over here, guess what happens to the loop, right? It disappears. So that is not much of a test.
I was more thinking of eigen and so on than of your timing example here.
Eigen has other issues. So the one thing I still need to solve with eigen, and this is also part of the GPU work, because you have the exact same problem over there. These complex templated libraries that produce template expressions coming out of there. In C++, what happens is when you do an assignment to something else, this is when the whole template collapses. So in eigen, you never do the calculation until the point where you need the actual value. It's not the only one that does that. There is CUDA, not related to this CUDA, I cannot pronounce it, it's the Russian CUDA, the bear. And there's several other implementations use template expressions, and using this through Cling with cppyy, what you get, if you don't know anything else, you just get a template expression that keeps on growing and growing, because when you do the assignment on Python, you just take a reference to it. And so where in C++ the template collapses, in Python it does not. So there is this undocumented feature, because it's not complete yet, where you can give cppyy a regular expression, which it will use when generating the wrapper, so that if the regular expression matches, you can specify a type it should collapse to. And so if you have, say on eigen, you have a matrix, an operator plus, and a matrix, and you get this template expression that contains the references to these two matrices and the fact that this is an operator plus, then you want to collapse this to a matrix. And this is what you can do this way to make this all work. And that's the big problem in eigen more than anything else. If you just start using it by default. The reason it's slow is because you get this enormous template expression that do not get collapsed until you actually generate a wrapper, and this is way down the line, and things go pretty badly down from there.
Okay, thank you.
So Wim, can you remind me what was the difference between CPython and PyPy? And
yes, maybe I should get my documentation up for that one. That's probably easier.
And maybe I have a faster question then in that case. So the 100 megabytes overhead in terms of memory, how do you measure that?
Top.
Sorry?
Top. The 100 is a nice round number. I don't exactly care about it because it's very consistent, the system, whether you have debug information on, how many of the standard headers that you have, because it really is the precompiled header. That is what is doing it for you. My main point is this is the order of magnitude. If you care about 100 megs, then 120 or 80 doesn't really matter. It also depends on what you actually use, because bits and pieces are collected. You don't get everything in one go. It's you use a couple of standard functions, it will start growing, and in no time you will hit roughly that mark. That is what it comes down to. It's my main point typically to explain people if they ask me, okay, what binders should I use? I'll explain the trade-offs. The numbers that I show for performance, I have a hard time beating Swig and built-in, as you saw, because there are these paths inside the Python interpreter specifically built for users such as Swig. So this is custom tailored in the Python interpreter, and how you're going to beat that, other than doing the exact same thing, which I don't want to do because you lose functionality. So let me just stop this here and grab the other one while I'm at it. And
I was thinking, can we bring that down in some case? Because if it's a startup cost, then maybe we can bring it down.
It's the precompiled header. So
Okay.
the only thing you can think of is to have very granular modules that doesn't bring in as much when you just do stud vector. That's the only thing you can think of. That's also the way that it will probably go. But modules and Windows. I need Windows. I really, really need it. I was mentioning the example of the architects. This is what they do. Most of them run on Windows, and they have a whole bunch of different packages that they're gluing together with Python, and it's complicated enough as it is. With the current setup, I'm finding all kinds of issues to them because they have users all over the place. All the Unicode stuff I was talking about came from that direction. Silly things, just having a space in the name, in the username, which Kling doesn't like, and on and on. There's lots of stuff that I found that way. So I really need Windows. So in structure, this is what I was talking about. I hope this is visible. It might be kind of small. So on PyPy, there's a package _cppyy, which is written in RPython. It has the equivalent in CPython, which is cppyy, which is written in C. And it's these guys that diverge because these have a duplicate functionality. The reason that this guy exists, _cppyy in PyPy, is because by writing in RPython, get access to the JIT. And you cannot get that at the Python level. And so this is why this exists the way. And then it's all the same again in the Kling backend and Kling itself. So this is where the differences come from in feature implementation.
Okay, and you need them both because they have different set of user bases.
PyPy is mostly a compatible product. The problem is that for the longest time, PyPy has been lagging in Python 3 support because people were not really interested. Now that Python 2 is officially, completely, utterly, totally dead, they're behind. And they're behind in Python 3, and Python itself in the on the Python 3 side has been moving places very rapidly, and so new features being added at the high speed, and the release cycle has been increased over the past few years. And the PyPy team is just too small to keep up. So if you use PyPy, you typically have a specific application in mind, and there's just fewer people using that than CPython. Separate from the fact that for most people who use CPython these days, they use it for bindings to call it the C++, meaning that the fact that the Python side of things is slow isn't really that much of a problem.
Okay, I see. Thank you. More questions? We have time for 1 or 2 more questions. Okay, seems not. Thanks again, Wim. It was a very...
Hello.
Okay, we
There's
have
somebody.
a question.
Yeah, I had a question on the implementation part of it. When you are returning my class, what exactly are you returning there?
This is a proxy.
Yeah.
So this is an actual true Python class. And it has a dictionary which has stubs for the functions, as well as properties, so Python properties for the data members. So it's an actual fully functional Python class with a full inheritance hierarchy, and everything looks Python-like on the Python side. And that is what you get back. It is only then when you do calls that more mechanisms and clean lookup start getting triggered in order to generate the wrappers, do a type conversion, etc. And the reason for doing that lazily is specifically that if you have a function that has arguments, and now all of a sudden, if you were to generate a wrapper before use, you can bring in whatever, because these arguments can be can pull in whatever other code.
So cppyy knows about, like, the Python part of it knows about the functions that my class has.
Yes.
Before
yes.
it's also that can like maybe give users like a lookup part of it.
Yeah,
like
this
auto
is another use. I mean, it was presented a couple of meetings ago for the D language. Underneath, let me go back to the other one. I know that the time is running short, but it's probably easier just to, where's my, here, this guy over here. This is where that information all comes from. You call into to Kling, and then it will provide you with the details of all the methods and data members that exist. And like I said, the actual lookup is then still deferred, but you have the names and you can represent stubs on the Python side.
All right, thank you.
And this thing, it's one of the goals, and this is Fazil can tell more about that, to clean this up and make this more widely usable than just for this purpose.
Okay. Thank you. We had a hand that was raised, Glass. Do you want to ask a question, or it was resolved in the chat?
I
It
think in
was
the chat
resolved.
said yes, Liz. Yeah.
I did not understand. Was your question resolved?
Sorry, yeah, we resolved it in chat. Thank you.
Okay, thanks.